Okay, thank you very much, and thank you for this opportunity to present the Netherlands. My name is Anna, and I'm with Qdnl, which is the Dutch National Quantum Program. And I would like to take a brief moment to explain what we do in the Netherlands and what our ecosystem looks like. So first, a little bit of history. Qdnl is founded in 2021. We are a non-for-profit backed by 615 million euros in government funding. And our goal and mission is to generate long-term economic value in the Netherlands through quantum technologies, of course. And the way how we function as a non-for-profit is that we connect government, industry, academia, startups, and international stakeholders. So we are really the coordinator and organizer in the ecosystem. Then a little bit about the Netherlands ecosystem. So geographically speaking, this is what it looks like. We have 5 different hubs in the Netherlands. And as you can see, all of the hubs kind of have their own specialties. So where Delft is really strong in hardware, Amsterdam is really good in software. And Leiden is, for example, very big on fundamental research and theory, whereas Eindhoven is good in materials and integrated photonics. So this is very complementary to each other, and many hubs also work together. Then a few things about the strengths. I won't list them all, but a few things that I really want to point out is, first of all, the scientific excellence. I think that we have a very strong fundamental research base. And later on in this presentation, I will also give the floor to QTech and TNO that can talk a bit more about that. From this very strong research base, we gained a very nice, fertile startup ecosystem. So as of today, we have 37 different quantum companies, some startups and some already scale-ups, of which some of them we have today as well in the Dutch pavilion. Internationally, we're very well connected, and we are trying to expand also our network to Korea. It's now our first time here, and we are enjoying a lot. And then I think the last thing that I want to name is the national initiative, Qdnl. It really, really helps that there is this central organization in the Netherlands that connects all of these different worlds, so government, research, industry together. And when it comes to industry, that is really the focus point at the moment in the Netherlands. That brings me to one of my last slides, phase 3. The first few years in our organization were really much focused on research acceleration, startup growth, and visibility and awareness spreading. We've done a really successful job in that, as you can see with the amount of companies that we have today, for example. But we think that the coming few years, since 2026, will be very important because we have these companies now, and now they have to get bigger. Now we have to connect them to industry. So that is really the phase that we're focusing on right now. I would like to end my presentation with an overview of our delegation. As you can see, we have a nice delegation with us today in the Dutch pavilion. It's just over there. It's the orange pavilion next to the Canadian pavilion. And QTech and TNO will give a little talk after me about what they do. But then we also have Qblocks, Quantware, and Delft Circuits. These are all Delft-based companies in hardware. So Qblocks is in control electronics, Quantware is in QPUs, and Delft Circuits is in cabling. So should you want to meet them, please head to the Dutch pavilion just over there. And then I would like to give the floor to Milan from QTech. Thank you very much.
Hello, everyone. Oh, excuse me. That's very loud. Which is the clicker? Is this one? And then to the next one. All right. Hello, everyone. Thank you for giving me the opportunity to briefly talk about QTech. So what is QTech? We are the Research Institute of Delft University of Technology. specifically focused on developing scalable prototypes of quantum computers and quantum networks. And we really try to combine academic excellence, so some of our researchers are the best in their field, together with relevance, which means that we are always trying to do research that is relevant to the world. We have a lot of spin-outs, some of them in the booth, like Q-Blocks and Quantware. And so we'll really try to create economic relevance for the Netherlands and for Europe. And then finally, leadership. So one thing that we're doing right now is building the first prototype of a European quantum network, because we saw that there was an opportunity there. There was no one really doing this, and we took this opportunity upon ourselves to build that. I have some slides to explain the pedigree of the research that we do at QTech. And so here you see the academic relevance of our institute. And you can see that when you compare all of the quantum computing institutes, that IBM obviously is very good. But then you see below that, together with MIT, there is QTech. And if you look at how our publications are ranked, so for example, if you look at the right column, that is the amount of publications in a top 10% journal, like Nature, Science, PNAS. We are the second most important institute. And if you look at the amount of publications, we are actually, that's the middle column, the most relevant quantum computing research institute in the world. This is a slide about our publications in quantum communications. And there again, across the field, you see that QTech delivers a lot of academic relevance. Something that we're really proud of, and that's also part of the reason why we're here in Korea, a country that has such a strong semiconductor industry, is actually at QTech we're doing a lot of research on semiconductor spin qubits. So these are qubits that are working on the same kind of material stacks that we use for ordinary computing, but then they do quantum computing. So this is something that we're really proud of, and then, yeah, I think the numbers speak for themselves. And also something else I'd like to highlight, when it comes to quantum networking, there is the phenomenon of quantum teleportation that is perhaps familiar to you. So already 100 years ago, in the first days of quantum mechanics, there was this idea that perhaps there's something such as quantum teleportation. And famously, this is one of the things that Einstein was really worried about. Like, quantum teleportation should not be possible. And actually, QTech is the research institute that was the part that proved Einstein wrong. Because we had successfully demonstrated a quantum teleportation over a distance of 1.7 kilometers, and later actually increased its length to 15 kilometers. And actually Jiwon, who will be speaking later, was part of the same research group that led to this incredible result, where we used existing fiber optic cables of our Dutch telecom provider and actually transported single photons to a node in the middle, entangled them, and then brought them back again. So, something that we're quite proud of, as you can imagine. At QTech, we don't do research alone. So we do research together with big partners, such as Fujitsu, with whom we research now how can we combine traditional supercomputing systems with quantum computing systems. So how can we create this hybrid quantum high-performance supercomputer? With Intel, we're working on cryo-CMOS. So that's how much of the control electronics can we actually bring into the cryostat. And then with Microsoft, we've done some really interesting work in developing a totally new type of qubit that's called a Majorana qubit. So that's, in a way, the perfect qubit in that it's very, very stable. And eventually, we hope it will become a topological protected qubit. Finally, when we talk about collaboration, actually those big companies are very important to us, but the most important collaborations are the ones with the startups that we created here at QTech. So in the left slide, you see 12 companies. Those are startups that came out of the research that we do at QTech. And actually, we've created in Delft somewhat of an ecosystem. And we see now that there are other quantum companies, such as Blue Force or Equal1, that are coming to Delft and work together with us. And I would like to end with this slide, because this is also an invitation for you. like anyone in Korea, Delft is open to do research together. We are very familiar to collaborate, and our doors are always open. So thank you very much for listening.
Hello, everyone. Yes, so I'm the final speaker from the Netherlands. I come from TNO, which in Korean I will say it is like 과학기술연구소. So here we're actually an institute with a revenue of about 680 million euros and about more than 4,000 researchers who are all researching to develop the technology for the industry. TNO itself is an institute that is here by law. So by the Dutch law, we have made this TNO Institute to bring technology that comes from university, like new science coming from the university. We mature it to be more compatible for the industry to use it. So we try to, like for example, if a new physics come out, we try to make that into a product. So we have strategic collaboration on the quantum side, especially with TU Delft. So QTech, that just had a presentation right before us, is actually started as a collaboration between TU Delft and TNO. And from QTech, as Milan just very kindly explained, was able to produce a lot of great scientific results out of this collaboration. And furthermore, also a lot of spin-offs have came out from all of these research results. For example, there's like QBird, which is being a prominent company in quantum communication. QBlocks, who is doing a very good role in doing quantum control electronics. Orange Quantum System, who is working on validating quantum processors, and Quantware, who's building these quantum processors. So in TNO, like one of our goal is to really mature the technology to, in the end, try to build these new companies that can make actual value to the general public. So what do we do in the quantum technology department in TNO? So what we do is we start from the very basics, like from nanofabrication to make devices, from material, and further on we want to do all of the research going from quantum computation to quantum communication to quantum sensing. So I'll give you an example of what the efforts that we are doing in all of these three divisions. So I'll first give you an example of the efforts that we're putting into the quantum computational side. So here we have a project called Quantum Inspire, and the main goal of this project is to build a quantum computer, in our case based on semiconductors, try to connect it to the internet cloud such that every users all around the world can access this quantum processor via their own computer. And the research that we do in this field is that we start from the material science with collaboration with TU Delft. We build a processor, we build all of the electronics or the electrodes on top of that device on our side. And then we also do the software on top of it. So we try to really do the full stack from the device side to the control to the software, and then in the end such that every end user can, via the internet, access our quantum system. Also, we try to expose this quantum technology to the general public. So what we do is we have this quantum testbed facilities. So in this case, what we do is we have a dilution refrigerator where anybody who has a device that they want to characterize, they can fabricate their device from their own lab, they can bring it to us, and then we can measure the device in our facility in our own dilution refrigerators. So we're trying to make these test beds as open as possible such that we can collaborate with many other people who are interested in quantum but doesn't have the full capacity to access to all of these expensive instruments. Furthermore, we also have a lot of efforts on the quantum communication side. So on the quantum communication side, we're trying to make a European-wide and also a global quantum network based on satellites. So we're trying to make quantum communication possible via a single country in the project from the Netherlands to, for example, like Greece, by communicating through satellites that are existing in outer space. Finally, we have some efforts that we're doing on the quantum sensing side. So on the quantum sensing side, we're trying to use diamond MV centers as our sensors, which in principle is we're trying to use a single electron to measure what's happening in the surrounding of this quantum device. Based on this principle, we have three types of instruments. One is a scanning probe microscope, one is a wide field microscope, one is a compact magnetometer. And using these three types of instruments, we're trying to address as much as possible use cases that are already in the current industry. So this is also a test bed. We're trying to open up these instruments to the general public for different industrial partners or academia partners, such that they can come to us, they can try these instruments, and see how they can make use of this new quantum technology. So some use cases that we already addressed together with industrial partners, one of it is semiconductor metrology, where we worked together with a graphene semiconductor company called Black Semicon or Melexis. They brought us a semiconductor device. We bring it into an instrument that exists in our own lab, and together we try to measure a challenge that they weren't able to resolve with the current instruments that they had in their own company. Another example is battery. In this case, we were able to collaborate with Toyota, who was interested in how their car batteries work. And then we tried to bring in the quantum technology into the car industry to see if this quantum sensor can actually help improve these batteries that goes in cars. We also had efforts in the infrastructure where we worked with an infrastructure company called Alliander. So it's similar to Hanguk-Jeolyeok in South Korea. And together we were using this diamond sensor to try to measure where the electrical line in the city exists. So we were together we were trying to see the underlying electrical power grids that were very difficult to measure otherwise. And finally, we also have a lot of collaboration with defense, where we try to use these very sensitive devices to help the precision of GPS, to help to know where your location exactly is by measuring the Earth magnetic field and finding the exact trajectory that your plane or car has passed through the whole process. So these are some examples that are happening in TNO. There are also many more quantum activities that are happening here. And one thing that I want to make sure is that we are very open to all collaborations, industry or academia, and we would like to together take the effort and make this quantum technology really be useful for everybody who are sitting here now. Thank you.